We are almost ready to move to the second step, in which we'll actually build a machine learning model using the estimator API from TensorFlow. But before that, let's just quickly summarize the machine learning problem setup. Remember that we are trying to predict the y variable, that is the total fare amount, and we're going to try and predict this y variable using various x variables which correspond to the pickup and drop off points as well as the passenger count. So this is a regression problem which we are about to go ahead and try and solve in TensorFlow. Before doing that, as usual, let's set up a very simple benchmark. This simple benchmark is simply going to be the mean fare amount divided by the mean trip distance. That will give us a rate. That rate multiplied by the distance of any one trip can be used as a very rough predictor, as a very rough estimator of the fare. This is a way of saying, let's just calculate the per kilometer rate on average charged by Uber and use that per kilometer rate to predict how much this particular trip will cost. We will use this very crude method to come up with a root mean square error that will then serve as our lower bound. Hopefully, no model that we build after this should have a worse RMSE. Well, in fact, we shall see that many of our initial models will actually perform worse than this crude method, but after a good deal of refinement, we will do a lot better. In any case, we are getting ahead of ourselves. Let's come back to this crude benchmark. Let's start with a simple helper function which gives us the distance between a pair of points. So this formula, which is known as the Haversine formula, makes use of some coordinate geometry in order to estimate the difference, or rather the distance between a pair of latitude and longitude locations. This simple function is invoked in turn from another function called estimate distance, and a third function which is very relevant to the calculation of the RMSE is the compute RMSE function. So given an actual and a predicted value, it calculates the differences between those two tensors, squares them, and then calculates the square root. That of course is the definition of the root mean square. We have a function called print RMSE which takes in a data frame containing all of the raw data, the rate that is calculated in the simple crude manner we just described, and prints out in a nice formatted way the RMSE. Then follows a little bit of simple code setting up the features and the columns and so on. And finally, we are ready to actually calculate our benchmark. We first read in data from our training, validation, and test data. We store the resulting data points into three data frames called df train, df valid, and df test. We calculate the rate as simply the ratio of the average fare amount to the ratio of the average distance. Notice that we do so only using the training data. So this rate is calculated only on the df underscore train data. We do not take into account the validation or the test data for this purpose. Let's go ahead and print our RMSEs on the training, validation, and test data. And when we do so, we find, as expected, that the three RMSEs are not all that different from each other. Why is this not a surprise to us? Well, we have chosen a really simple and crude model. A model like this is likely to have very little risk of overfitting, very little risk of high variance. And so the fact that the RMSE on the test and the validation data are smaller than that on the training data is mildly reassuring. In any case, of course, this was not a serious model at all. Let's go ahead and set up a benchmark. This will serve as a common benchmark which we will use whenever we have a model that we want to evaluate. We will calculate all of our RMSEs against this benchmark for the different iterations of the model that we build. We will construct this benchmark with a query very much like the one which we just created, where we filtered out all of the outliers and the data points that we did not want. The only bit worth keeping in mind here is that we take into account two phases. Phase 1 is the training phase and phase 2 is the validation phase. Depending on whether we invoke this function create query with phase 1 or phase 2, we will end up picking either the training data or the validation data. The second parameter that we pass in also tells us whether this is going to be used to sample the dataset or whether it's going to pull the entire dataset. If the value of the second argument, every underscore n, is equal to none, then we are basically going to pick up the entire training or validation datasets. On the other hand, if the value of every underscore n is not equal to none, then we are only going to sample some proportion of the data. In any case, let's now go ahead and invoke this method. We are going to pass in the phase as equal to 2. That means this is validation data, and we would like to sample 1 in every 100,000 rows. When we run this function, we get back the validation data set that we are going to use for benchmarking. And the RMSE on this simple data set with this very crude measure is 8.03. Let's go ahead and see how much better we can do with a real model. Let's switch over to TensorFlow and make use of the estimator API in order to do so.